Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and privilege to be serving you here today as it is every day in my virtual classroom. If you step on inside the virtual classroom here, we are going to be reviewing things regarding, well, intervals within functions, domain and range, and behavior, max, mins, increasing, decreasing, a lot of little things regarding what you can find on a graph and how you can write out the characteristics to help identify them the way that the math gods want us to. That's the whole goal of this thing. I have a PDF that associates with the thing that you're doing here. For my classes, it's a practice quiz on 2 different sections there. You can download it in the description section and play along with me, see how you do. All right, let's take a look at it right now to save time here. And we are going to be starting by looking at number 1, excuse me, which we have 3 items written in what's called interval notation, and we are going to rewrite them using set notation or inequalities. Now with my kiddos, I'm ignoring the whole set like, there exists an x such that whatever. I'm just writing the part that's inside, the inequality in and of itself. And for the sake of just doing that for my kiddos, I'm just going to say that right here. That's going to be the important aspect for me. Let's use x as the variable. Now, in all 3 of these things, you're going to either see square brackets or parentheses surrounding 2 numbers. Those 2 numbers are your lower bound and your upper bound. How small your value goes, how high your value goes, even if they go all the way to infinity and beyond. Now, the square brackets means that that value is included as a part of your solution set, and parentheses mean they're not included as a part of your solution set. So this is where you'll see things such as like the greater than, less than, or equal to's, and here's where they'll just be greater than, less than, right here. So when we're using the x variable and we either write a compound inequality or a normal inequality, make sure that we understand that as far as including it. On all these problems for you guys, just to help you out, I'm also going to draw this on a number line. That's not a requirement if I'm going to do that for my students. It's not part of the instructions. But I'll also draw these on a number line to just help make sense of what it is we're looking at and how the inequality kind of reflects what it is that we're talking about. Okay, so for number 1, part A here, we do see that we have a lower bound of -2 and an upper bound of 10 that our x solution set goes through. Now, -2 is apparently included. What that means is there's a closed circle there on -2, and 10 has an open circle, and x, the variable, can be anywhere in between those two. X can be between -2 and 10. Now again, this number line thing is not a requirement in any stretch of the imagination for what we're doing here, but this idea might help coincide with what the heck this means versus this, and what the x is doing here, and how we can actually write that inequality. So how do we write that inequality? As what's called a compound inequality, which means on a single line, we're going to have actually our lower bound written, our upper bound written, and x sandwiched between them. -2 is less than any x value, which is less than any 10 value. -2 can be included though, right? X is greater than or equal to -2, so we include that. X is less than 10, we don't include that. And that is the end result. Yeah, if you include the set notation, the curly braces and stuff like that, we can have that. But this is indeed the equivalent to this, but in a different notation. They both mean the same thing. Just this is inequalities, this is interval notation. And we're going to be using both here later. All right, this one here, it goes from -infinity all the way up to 0. So if 0 was right here, 0 apparently is not included, as the parenthesis indicates, and that is the upper bound. That is the rightmost that this thing goes on this graph, and then it goes as far left as -infinity, which means it goes forever in this direction there for x. Forever. That's an arrow. That's not a closed circle. So x goes forever to the left there. How do we say this as an inequality? It's not a compound inequality. We don't need to use infinity on it, or -infinity. We just compare x to it. X is any number that's less than 0. X is any negative number. So we just say, hey, x is less than 0. That's it. This needs both bounds. That's why we need the -infinity. But when you have the variable here to compare to something, and there is no other end in sight on the other end, we don't need to set its restriction. All right, C, we're going from 3.14 to 31.4. So like if 0 was here, this is 3.14. Hey, that's like pi in approximation. Here's 31.4. X is between 3.14 and 31.4. That means 0 is not included. And because they're both square brackets, that means it's a closed circle on both of them. Once again, not something we're doing for number line stuff, but I will be talking about closed and open circles later. So I hope that that makes sense, that closed circles are included, open circles are not. X is between them. So how do we do this here? Once again, like part A, we're going to have a, a compound inequality here, where the lower bound is 3.14. 3.14 is less than or equal to X, as it's included. 3.14 counts, and 31.4 also counts. X is less than or equal to 31.4. Any number between 3.14 and 31.4, inclusive, meaning including 3.14 and 31.4, are solutions for this set, whether written in interval notation or set inequality notation. And that is number 1, A, B, and C. Okay. Number 2 is the exact opposite. This time we have the quote-unquote set notation, and we're going to write them in interval notation. Now that you've kind of heard a lot about it, I hope we can kind of start to make sense of the idea of what the bounds mean, what the parentheses and square brackets mean, and maybe even go without the number line all said and done. I'll do it on the first one with you. You know, I'll stay consistent. Let's keep doing number lines. You've kind of felt that out. Maybe you can help make sense of it that way. All right, X is between negative 20 and 20. So here's negative 20, here's 20. Hey, here's 0, just for good measure. And X is in between them. Now, negative 20 is not included, so I'll do an open circle. 20 is included. It's also equal. X can be equal to it, so I'll put a closed circle there. And there's your X. Now, interval notation means we got to do this thing right here. So we have a lower bound of negative 20. We have an upper bound of positive 20. And the parentheses or square brackets will let us know whether those values are included or not. Negative 20 is not included. It's strictly less than, not less than or equal to. So we're just going to use a parenthesis. 20 is included because equal to is a part of it. So we will use a square bracket. Again, number line, whether or not you put it, it's up to you. Not a part of the answer. This is the answer. All right, part B, X is greater than or equal to 2. So as a number line drawing here, as a number line drawing here, we're just looking at, hey, here's 2, here's 0. I always like to put 0 on my number lines. It just shows where we're going with it, especially if we were solving especially if we're solving inequalities. And coming up pretty soon, maybe next week, you're going to see me algebraically solving some inequalities as well. So this graphing stuff doesn't really go away. I think it's actually good that I'm doing the number lines. Anyway, X is greater than or equal to 2. Closed circle on my boundary point of 2, and greater than means anything that's larger than it. 3, 4, 1,000. That's an arrow, by the way. And here's X. Let me not do my arrow as solid. You might think that's a closed-end thing. Let me just draw an arrow. There we go. X is greater than or equal to 2. It goes on that side. That's not what we're trying to do, though. We're trying to write interval notation. But this does help us understand what the left bound and right bound are. My left bound is 2. My lower bound, I should say. That's as far left as my graph actually goes. As far left as 2. So 2 is on this side. How far right does this go? Forever. We do have to include that right bound, though, and call that in positive infinity. That is the bound which we actually never reach. So how do we talk about this? It does reach and touch 2. It includes 2. We put a square bracket on that bad boy. And it does go to positive infinity in the way that it trends toward it. We never actually reach it. Remember that? So we always put a parenthesis around the positive infinity or the negative infinity, what have you. You saw one right here with a parenthesis there. That'll always be the case. All real numbers. You know, it's really hard to do a number line for that because it's just arrows that go both ways, basically. All real numbers means every number under the sun is hit. So how do you say that in interval notation? Well, what is the lower bound? You might say there is none, but really our way of saying that is we go toward negative infinity. So negative infinity is the lower bound. I'm going to write that on the left side. The upper bound is positive infinity. It goes forever to that direction. So there we go. Negative infinity, positive infinity. And just like I said, parentheses around these things because they're not included. Remember, infinity is not a number. We don't actually ever reach infinity. We just get closer and closer to it. Not truly. You know what I mean? We just keep going to the ends of Earth. But that's what this thing means here. It's all real numbers. Okay. All right, so that's numbers 1 and 2. Hopefully we're kind of making sense of this inequality and interval notation because we are going to be using these as often as we can. And here's what I tend to do, guys. For domain and range, whenever they request domain and range, I tend to use the inequalities. It's a personal thing for me. I just tend to. So I guess I will just do that here. For the notes on increasing, decreasing, pretty much everything else, especially for lists, I tend to use interval notation. We'll see if I go interchangeable based on what's there, but that's what you'll probably see me do. All right, here we go. Continuing on to number 3, where we have parts A and B. We have 2 graphs, and we are going to identify the domain and range for each of them, and also the end behavior for these two functions as they are pictured below. I have a nice exponential function here and some oscillating, probably periodic function right there. Now, 2 notes. You may use set or interval notation to list the domain and range, kind of your call. I'm probably going to be using the set notation inequalities. Remember, if something is all real numbers, you can say all real numbers, by the way. And then if there isn't left or right end behavior, you can indicate that there is no end behavior there to the left or to the right. Sometimes there's just no end behavior on one direction, and the other direction there is, and you're going to have to make sure to tailor that. All right, on part A, I have this exponential function here where it takes off, shoots up there, up and to the right, which is going to be something we kind of make mention of. And then to the left, it goes to the left forever, and it's going down forever, but in its own way. It's going closer and closer and closer to -3, but as you kind of see this asymptote right here, this dotted line, it says, I'm not actually going to touch or pass this line. You might say, hey, it's touching the line right there. And this line's really thick. If you actually saw this as a graph, you'd see that it's actually just getting closer and closer, and it's really just staying above it. I indicate that actually when I draw this with a half arrow. The arrow in itself indicates it's going forever, but the half arrow is saying, I'm not truly like going down forever. It's not like it's doing that. Just making sure you know that. All right, domain, guys. Where does this thing go? Does it go left forever? Does it go right forever? Yes to both. It does. We go from negative to positive infinity. My inequality version of it, not even truly inequalities. I like to say all real numbers. Sometimes you'll see me use that all real number symbol. It's not a perfect version of it. Otherwise, you can do like a negative to positive infinity. Range is a little bit of a different story here, and because we're limited in the range. It doesn't hit these negative numbers below -3. Heck, it doesn't even hit -3 if we're going to be, actually specific about it, which we need to be. But it does go up forever. It goes up forever. There's no upper bound. It goes toward positive infinity, but the y values get clipped once you hit -3. Heck, we don't hit -3. Our range is y is greater than -3. Every y value that you'll see on here is greater than -3. Not equal to. Doesn't count to be equal to. And nothing lower than that either. All right, end behavior. This does have end behavior because it has an all real number domain. So we go to positive infinity. We go forever to the right here. And it seems like we also go forever upward toward positive infinity. So as x approaches positive infinity, y approaches positive infinity. And as x approaches negative infinity, as we go forever left here, it's starting to converge closer and closer to -3. Remember, the arrows mean what it approaches. It never actually equals infinity, just like it never actually equals -3, but it sure approaches it. It sure gets closer and closer to the point that you kind of say it might as well be. That doesn't mean it is, but when you say it might as well be, that's the idea of approaching. As we go forever left, we're getting to -2.999999999, and I'm not joking. It does that. It just never truly is -3, but it does approach it. Okay, that's part A. Part B, we have this graph that has some funky stuff going on, and it's a good one to talk about when we talk about mins and maxes and stuff, but that's not what this problem's about. It's about domain and range. Now, domain is asking how far left and right does this graph go. Looks like it goes as far left as -3, right? It goes as far left as -3, and then it goes as far right as apparently 2. Now, there's a closed circle on -3, which means x equals -3 is a part of your domain. It's actually included. As a compound inequality, I can start to say that, for example, x is between -3 and 2. Now, there's an open circle on 2, which means 2 is not included on x. What I'm saying, x equals 2. It's not included. 1.99999 counts, but apparently 2 does not. So your domain is everything between -3 and 2. -3 is included, 2 is not. That's how far left and right this graph goes. How far up and down does this graph go? This graph goes, it's limited. It goes as high as y equals 4, right? It goes as high as y equals 4, and it goes as low as y equals -4. Now, with this open circle, you might say, well, look, y equals 0 doesn't count. But hey, y equals 0 does count right here. So there is a y equals 0 that exists. It goes you can find every y value here between -4 and +4. So we get to write that as a compound inequality, just like we would ordinarily with the other ones, between -4 and +4, and they are both included as well. Right? I actually hit -4 here and here, things like that. So that's my range for that. End behavior, we want to look in terms of, in long term, as we go toward positive and negative infinity, if these graphs went forever and had an unlimited domain, infinite domain, they don't. They clip. There is no end behavior on this. Just because these terminate doesn't mean we're referring to what the actual math definition of end behavior is here. No end behavior. No, we're not going to state why, but we just did state why. Nothing to say. Nothing to say on that. We're done on that one. All right, that's the front side of this. Now, the back side is going to really just kind of be two bigger problems. Actually, one's a challenge problem. It's really not considered as like part of the even quiz for my kiddos. It's more of like an extra credit variety. We'll get to it. But the first one is one graph, and we list all the details and characteristics about it that we can. So let's take a look. The function shown in the graph features several characteristics for which you will be identifying through markings and proper notation. Number 4 is all about marking up the graph a little bit. I'll show you what I mean. And then numbers 5 through, I think, 9 do the rest of them. Respond to the requested material below. On this graph, we are going to place the following letters here. We're going to place an M on every relative max and relative min that we find on this graph. Now, a relative max and relative min are the locations where the graph changes direction from increasing to decreasing and decreasing to increasing. Now, I'm not specifying which are which by using the letter M. We'll do that later on questions 5 and 6. No, excuse me, on questions 7 and 8 for max and min. But here, let's place an M every time we see those. So we go from decreasing to increasing here. This point references a relative minimum. So I'm putting an M there. Now we're going from increasing to decreasing. That's again another relative extreme. That's a relative max there. This goes from decreasing, it stops, it flattens out, and it goes to decreasing again. That's neither a max nor a min. Neither max nor a min, but it is not decreasing the entire time. I want to make sure that you know that. It's not decreasing the entire time. It goes from decreasing to increasing here. It changes direction, so that's going to be a relative min right there. Place another M. Increasing and decreasing right here, another max. Decreasing and increasing here, another min. So 5 relative extreme in total, 2 maxes, 3 mins, and we kind of carry forward. All right, so that's going to be the look of that guy. An O or a 0, I guess an O. An O on all 0, well, a 0 on all zeros of the function. But, just a big open circle. Even though it's not the same, it doesn't mean the same thing as open circles. Zeros are where your graph hits the x-axis, where it hits actual zeros when y equals 0. So it hits the x-axis here at the origin, it hits the x-axis here, and it hits the x-axis right here. It actually tangentially touches the x-axis there before it bounces back up. So an O and an M there at the same time. I'm basically going to circle around the M. Let's place eyes on intervals of the curve that feature an increase. Now, for my students, I have literally written the word increase or the words INC, the letters INC, to indicate it. So this is not an increase, so this is a decrease. So what we do is we look at the graph from left to right. We look left to right and say, is the graph going up or down at that time? Is it going up or down at that time? On this particular interval, it's going down the entire time as we read left to right. So we are looking at a decrease right there. I'm going to put a D there. Oh, sorry, D's on decreases. A D right there. It's increasing here. I'll put an I on the curve right there. Decreasing again right here. Now, it doesn't increase right here, but remember, this is where it flattens out. So you don't want to just put a D right here and leave it be. You want to put a D right here as well because it stopped decreasing right here. It actually stopped. It decreased, stopped, and decreased again. Okay. There's another increase right here, another decrease right here, and another increase right here. Again, you go left to right. Don't look at this arrow and say, it's going up, it's increasing. No, that's reading right to left. We got to read left to right on these things. Be careful. All right, so those are all the markings, and honestly, those markings may actually help you answer some of these questions. I don't know if they do, but to me, they kind of do, because now that I've labeled them, I kind of killed 2 birds with 1 stone. I see where it's increasing. Now I got to work on the notation of it. On which intervals is the function increasing? It's increasing between this min and this max right here. And now the intervals are the x intervals. From x equals -6 to x equals -4. From -6 to -4, it's increasing, not including -6 or -4. Now, I've mentioned that, in calculus and stuff, they say, hey, you're allowed to include them. I'm not a fan of saying that. I'll tell you it's acceptable, but you're not going to see me write it. So from -6 to -4, we're increasing. Where else are we increasing? By the way, this is interval notation. This is not including -6, not including negative 4, but from here to here. It's also increasing right here on this I from x equals 2 all the way to x equals 4. So from 2 to 4, you see another increase, right? From 2 to 4, you see the increase. Hopefully you're understanding what I mean when we're listing those. So from 2 to 4. And lastly, there's an increase at the tail end of this. And when I say that, I mean this graph goes on forever. But from 6 onward, you're seeing an increase the rest of the way. The end behavior is going up right there. So from 6 onward, it is doing that. So from 6 to positive infinity, you see an increase in the function. So the markings kind of help indicate it. And then we get to write them out right here in interval notation. You can use inequalities, but do you want to see me do this each time? Maybe you're saying yes, but x is greater than 6. I don't want to do that each time. That's kind of a lot. I like the interval notation. It's quick, clean, and contained. You know that it's x's. We move forward. On which intervals is the function decreasing? Now we look at the d's. So from here, remember this went left forever. It came from forever from the left. So from negative infinity all the way to negative 6 was a decrease. It was decreasing here the entire time from negative infinity to negative 6. So I'm going to indicate that. Definitely never never square brackets. It definitely never hits negative infinity, so we always put parentheses there. And then it decreases again from negative 4 to just to negative 2. Remember, at negative 2, it stops. I'm just going to put a little point there and just I'm going to put a little slash and bridge. It stops decreasing there for a moment. So from negative 4 to negative 2, it hits the plateau. And then from negative 2 down to, not down to, but it keeps decreasing from negative 2 to positive 2. Remember, I'm looking at x values. Negative 2 to positive 2, decrease again. Okay. There's one more, and it's from 4 to 6. From 4 to 6, we see our last decrease right there. So again, I think those markings kind of help. As far as, I give my students credit for marking them, and then I think it kind of helps you get that notation. I'm going to take away that slash now, though. All right, those are the intervals of increasing or decreasing. What are the relative maxima? When do they occur? What are the relative minima? When do they occur? So maxima is the plural for maximum. So I see maxima right here and here, right? These are the two maxes. When we go from increasing to decreasing, that's when they hit their relatively highest points with the region around it. Now the whats are the y values. The maximum is 7. The maximum is 2. They occur at the x values of negative 4 and positive 4. So I'm going to write those out. Okay, what are the relative maxima? There is a relative maximum of 7, and that occurs, when do they occur? It occurs at x equals negative 4. Again, the maximum is 7. It occurs at x equals negative 4. I know that's kind of confusing to people to hear, but the best way to put, because everyone understands money, the best way to explain it is in terms of money. If you were working a 12-hour shift and every hour you chart how much money you make, and then I ask you, what's the maximum you made in any hour? Then you might say, the maximum I made was, $90. You're not saying the maximum was hour 4, right? We're talking about the y value there. The maximum was $90. You say, oh, what hour, when? When did you do it? At what hour? At hour 4. In my hour 4, I made $90. But the maximum itself is the y. It's the 90. Things like that. I want to make sure that you understand that the what is the y, the when is the x. Now, there's another maximum here of 2 at x equals 4. The maximum, the y value of the maximum there is 2. It occurs at x equals positive 4. So those are my maxes. The mins are the other m's right here, the ones where we go from decreasing to increasing. This is a min, this is a min, this is a min. So let's write those 3 out right here. There's a minimum, remember these are called relative mins, relative maxes. There's a relative minimum, remember, it's not the lowest the graph goes. There's a relative minimum of 3 that occurs at x equals negative 6. There's a relative minimum of negative 4 that occurs at x equals 2. And there's a relative minimum of 0. On the x-axis is 0. There's a relative minimum of 0 at x equals, looks like 6, at x equals 6. Those are your 3 relative minima. All right, and that's kind of how, I don't know if that's the perfect writing. I'm using the @ sign, like it's like send me an email, or a Twitter, whatever message. But that's what we're saying. The what is the y, the when is the x. The what is the y, the when is the x. All right, number 9, parts A, B, and C. On what interval or intervals is the function positive and negative? And then what are the zeros of the function? Because there are no intervals for 0 here. There's actual, just single values. So on what intervals, again, we're talking about x intervals are positive, negative, and 0. There's a difference between positive and increasing. Increasing means going up. Positive means above the x-axis. So which intervals are positive? Let me kind of box it out for you. I did this from one of my other homework videos for you. Hopefully it kind of makes sense what I'm going to do here. I'm going to kind of give you a boxy figure and say, you see this whole area right here, guys? This function is positive in this whole area right here because it's above the x-axis. It's above, it's above, it's above. And then it hits a 0 right there, and then it goes below, right? And then it hits a 0, and then it goes above again right here. And then it hits a 0, and then it goes above again. But it does hit that 0. So it's not above the entire time here because it hits a 0. But these are the intervals for which it's above. Forever left, all the way up until x equals 0. And then between 3 and 6 on x, and then from 6 onward. It's above in all of those instances. So we get to write those. I could use interval notation again if I'd like to, and I will choose to here. So it's above the x-axis for all those moments. We are going to be having those positive between negative infinity to 0 on x. We're positive the entire time, even though it's decreasing. Sometimes it's almost decreasing the whole time. From negative infinity to 0. Now, do we include 0? No. 0 is a 0. That's actually where it hits neutral ground. It's neither positive nor negative. And we'll be indicating that for what are the zeros. It's also positive again from between x equals 3 and x equals 6. Again, not including 3 and 6 because 3 and 6 are zeros like that. I'm going to get rid of those now. 3 and 6, or from 3 to 6. And then from 6 onward. Remember, not including 6, but I mean after you hit 6, onward to positive infinity. We saw that it goes up forever. As far as end behavior goes, forever right, forever up. All right. On what intervals is the function negative? Basically anything else. This dip right here is where we get a negative portion of the function. Red doesn't mean bad. It's just indicating in terms of this red thing. It's negative there from 0 to 3 on x. From 0 to 3, you get negative y values. Negative y values underneath. Underwater, if you will. So from 0 to 3. Single interval, non-inclusive for those. What are the zeros? Those are the x values for which we hit the x-axis. We hit the x-intercepts. You get an x-intercept here at 0 and at 3 and at 6. It does tangentially touch there, as we've kind of mentioned before. Those are the 3 zeros. Heck, we already marked them with the zeros right there, so I don't know why I'm doing that right now. Those are your 3 zeros. They're x equals 0, x equals 3, and x equals 6. Okay, guys, so that is the crux of what this thing is all about. Now, there's kind of an open-ended question at the end here, and if you feel like tuning out at this point, I don't blame you. It's going to be a part that's going to be a little tough for some people. You know, they're going to get lost on it a little bit. It's a challenge when it comes to my kiddos quizzing. It's going to be an extra credit question. But I'll let you know what, these are the fun logic puzzles. I don't have an equivalent that I have right now, but I can think of those riddle things where it's like, there are 6 kids standing, like in a line together, and you're trying to figure out where they stand, right the order they stand, where they're like, Ricky is 2 left of Bobby, and he would never like Lisa. And then like Lisa is 4 people away from Stephanie. Like, that thing? And you try and, it's a little bit of trial and error. And my only problem with this when teaching this part is I had to make a graph beforehand to know what information I wanted to give. So I already know what the graph looks like. So I'm going to try and best approach it from a way that I'm like you. I'm investigating it as I go, and I'm working it out. The good news is, despite the trial and error, you'll know when you contradict yourself. All the information that's going to be given here has so much overlap, meaning you don't actually need all of this information to get this answer. That when you do some of these things, the overlap in the other things that are stated help confirm that what you said was actually kind of correct. Okay, but I will kind of hit some of the nitty-gritties and go down the list and see where we can work things out and get some for sure points. And then what we can do with the rest of the behavior. For example, domain and range right here. I like knowing that the domain's all real numbers, and the range might help as well. Y is less than or equal to 5 to know when I kind of hit a top point. But when it says y is less than or equal to 5, that also means there's probably a relative maximum of 5 somewhere if that's also hitting a top point like that. Maybe. We'll see what else goes on. But domain is all real numbers, range is y is less than or equal to 5. That means it goes, for all we know, the graph might look like this, right? But again, we don't know, so don't just draw things straight up. Just keep this in your back pocket, you know? Now, the function is positive. I'm going to do the little box thing again to show you this here. The function is positive from, where is it? From -4 to 0. From -4 to 0, we are going to be looking at positive. We're going to be looking at the graph above here somewhere. It's going to, you know, do some stuff above. But then it's negative from -infinity to -4. This is actually fun for me to kind of do on my own and investigate. Because now I suddenly can't picture the graph anymore now that I'm doing this. From -infinity to -4, you see negative territory. It's underwater here. And then it is again from 0 to 2. We're looking at x when I say these things, by the way. Hold on. Give me one sec. From 0 to 2, it's also negative right there. And then from 2 to positive infinity. Now that sounds weird. Why didn't I just say from 0 to positive infinity? Well, if you remember from the last graph, there's potential in it just hitting a 0 on 2 and then going back down. So now we see the regions. Remember, it's a domain of all real numbers. Oh, let me do this with this top part here, by the way. We know the range only goes as high as 5, so I'm going to do it like that, if that's cool. It only goes as high as 5 for sure, but these might go down forever. You never know. Okay, so there's that. The zeros are at x equals -4. So these are official, guys. These are official points on our graph. This is actually a point on our graph. At 0, this is a point on our graph. And 2, this is a point on our graph. And that seems to coincide with what we talked about with positives and negatives. Somehow, guys, I think the graph is probably going to be doing something like this. That's a behavior that you can start to kind of play with. Now, obviously, somewhere up here, it's probably going to have to hit 5 in this region, too. Don't forget that. This is, you know what? This is kind of fun. Only you probably don't get to make boxes like this because, you know, there's that. All right. It's increasing from -infinity to -2. Now, this is an important concept here. It's increasing from -infinity, now remember, -2 on x. So all the way up here, it's increasing the entire time, which means that, you know, the graph could be doing something along the lines here and increasing. Now, at some point, it's got to start decreasing. It looks like it does it from -2 to -1. These aren't official drawings. From -2 to -1, it does some sort of decrease there. So we talked about the fact that it hits as high as 5, and you're going to start seeing some other information here, like there's a relative maximum of 5 at x equals -2. So instead of drawing things early, maybe you want to find some other points that this hits. But it looks like it does go up and through here. That makes sense. But it has a relative maximum of 5 at x equals -2. X equals -2, it has a maximum of 5. This is a point that's on your graph, right? This is a point that's on your graph. I've never said these were in order, you know, that like, hey, do this in this order. I haven't even really looked too much at this, like in big full amounts. Relative maximum of 0 at x equals 2. X equals 2 is a maximum of 0. So here's something you do want to do. You know that this is a maximum of 0. That means that it does this right here. And that kind of makes sense because these are negative territories. It's a maximum right there. It bounces and it goes back down. Okay, cool. And there's a relative minimum of -2 at x equals 1. At x equals 1, there's a minimum of -2. So it hits down here as well. Okay. So it's decreasing, let's see. And then end behavior. Okay, end behavior. Last thing I want to mention here. As x goes forever right, y goes forever down. And as x goes forever left, y goes forever down. So, you know, we kind of also understand this notion right here, that it's going to be doing the forever bits here. I think we can officially get some points in drawing this graph now. Let's take a look at the maxes and mins again. Or the increasing, decreasing again. It increases from -infinity to -2. That seems to make sense because at -2, you hit that increasing, sorry about this, increasing up in forevs like this until we hit -2 right there. And I don't mind you drawing bends like actual cornering instead of actual curves. And then it decreases from -2 to 1, to 1. So it hits a decrease right here. It has to go through that 0 and it decreases down to there. And then it increases again from 1 to 2. Like that, 1 to 2, and then it decreases again from 2 to positive infinity, so it decreases the rest of the way there. That seems to be the graph. Let's see if anything contradicted, but like I said, there's going to be overlap in things that are going to agree with each other with everything we said. Let's see if everything checks off. And this is it, guys. This is the last question, by the way. Let's see if everything checks off. Domain of all real numbers. Goes forever left and right. Check. Domain of all real numbers. Range y is less than or equal to 5. Does it ever go beyond 5 up here? No, it stays underneath, and it goes down forever. Check. It's positive from -4 to 0. Up above, yeah, within the boxes, we can check that one, and negative, it's within these boxes here. Sorry if my picture's kind of in the way here, but check that one up. The zeros, we plotted those. X equals -4, and it goes through it. X equals 0, and it goes through it. X equals 2, and it goes through it. Check, check, check. It increases. This is how we drew the graph. It increases from -infinity to -2, and it stops increasing there. And it also increases from 1 to 2 on x. It does right there. Okay. It decreases from -2 to 1, and it decreases from 2 to infinity. It goes forever, right? So check. It has a relative maximum of 5 at x equals -2. That's what we plotted that point. A relative maximum of 0 at x equals 2. Okay, right there. And remember how it, whoops, I don't want to check right there. I'll do it right here. And then a relative minimum of -2 at x equals 1. Relative minimum of -2 at x equals 1. And check there. And lastly, end behavior, as x approaches, as we go forever right, we go forever down. And as we go forever left, we go forever down. Check. All right. This is kind of the only way, outside of what you do with these curves and stuff, this is really the only way to interpret this graph. Honestly, guys, that problem's more fun than I kind of took credit for now that I started to navigate through it. I really did enjoy kind of doing that one, and I hope my own students do as well, and I hope you enjoyed following along with that. Let me erase, though, these guys here, because that's not realistically a part of what you would draw. There it is, guys. And that ought to do it for this one. Thank you so much for watching Mr. Robinson's Virtual Math Classroom with this review. I hope it made sense. Leave any comments down below if you have any other questions. Thank you, and take care.